Hello my friends and welcome back to the You Can Do TV channel. The installation of 2 Lagerway wind farms in Finland, with a combined capacity of 27.5 megawatts, involved the delivery and assembly of 5 complete wind turbines. Each turbine's major components, tower sections, nacelle, hub, and blades, were transported to the remote finish sites using specialized heavy-haul equipment, ensuring safe handling despite the challenging weather and terrain conditions. Central to the efficiency of this project was the MST modular steel tower system, which allows tower segments to be assembled on-site rather than transported in full length. This modular design significantly reduces transport complexity, minimizes road modifications, and enables access to sites with limited infrastructure. Once on location, the installation sequence began with foundation preparation, ensuring precise anchoring and alignment for the tower base. MST sections were lifted and bolted together using high-capacity cranes, creating a rigid, stable structure capable of supporting the heavy nacelle and rotor assembly. The nacelle, containing the generator and gearbox, was then hoisted into position, followed by the rotor hub and 3 precision-balanced blades. Electrical systems, including power cabling, control wiring, and grid connection equipment, were installed in parallel with mechanical assembly. Safety systems and monitoring equipment were also integrated to ensure compliance with operational and environmental standards. Despite the scale of the operation, the MST system allowed the complete installation of all 5 turbines in just 2 weeks. This rapid assembly not only reduced on-site labor time and costs, but also minimized environmental disruption, enabling the wind farms to begin clean power generation quickly. The Helmke Coil Shop in Germany specializes in the engineering, manufacturing, and testing of high-voltage diamond coils, auxiliary windings, and low-voltage winding kits for industrial applications. The production process begins with advanced product engineering, where reverse engineering and performance upgrades are carried out using computer-aided design, CAD. This stage includes optimizing the insulation system and evaluating electromagnetic, mechanical, and thermal characteristics. Each design is aligned with HELMKE's internal technological processes and quality control protocols, certified to ISO 9001 and ISO 14001. In-house coil manufacturing utilizes a comprehensive range of automated winding, shaping, and taping machines to ensure precision, repeatability, and adherence to strict industrial standards. The insulation application process is also fully controlled in-house, with available technologies including unpressed resin-rich, hot-pressed resin-rich, and vacuum pressure impregnation VPI systems. This flexibility allows for tailored solutions that meet diverse operational demands while maintaining consistent quality. Quality assurance is reinforced through rigorous testing of every coil, performed in both flexible and fully cured conditions, exceeding standard industry requirements. The testing phase ensures that mechanical integrity, insulation quality, and electrical performance meet or surpass operational specifications under various load and environmental conditions. Installation is carried out by a specialist team of winding technicians, skilled in placing rigid high-voltage coils into stator slots while maintaining the insulation's layered structure. HDPE's track record in machine overhauls and rewinding projects ensures reliability and long-term performance. For projects requiring additional expertise, on-site rewinding support and training are available through HDPE's international technical staff. This service provides direct guidance to ensure correct installation, alignment, and insulation preservation during field operations. By integrating precision engineering, automated manufacturing, controlled insulation application, and stringent quality testing, HDPE delivers high-performance coil solutions designed for operational efficiency, durability, and compliance with the most demanding industrial environments. The combination of technical expertise, state-of-the-art machinery, and global service capability ensures each coil meets exacting performance standards.
Oregon's lush Douglas fir forests and long-standing timber industry give rise to a groundbreaking innovation, mass-ply panels (MPP). Developed with a vision for sustainability, MPP begins with responsible forest management in the Santiam Canyon, where engineered wood firm Freres ensures long-term timber supply through sustainable harvesting. Once harvested, logs are transported to high-tech facilities. Here, they're peeled into thin veneers, layered crosswise, and bonded using heat and pressure to form strong, uniform panels. CNC machines then cut structural components with high precision, enhancing efficiency and minimizing waste. The robotic wooden pallet assembly system by Robotic Automation utilizes 3 Motoman industrial robots, each with a 180 kilograms payload capacity to deliver high-speed precision pallet assembly with full flexibility in pallet formats. Integrated with advanced safety guarding, light curtains, automated nailing systems, and in-feed conveyors, this system ensures synchronized operation with upstream equipment. Capable of producing up to 75 pallets per hour, it offers exceptional throughput within a compact footprint. The fully customizable design accommodates various pallet sizes while improving hygiene, structural uniformity, and manufacturing efficiency.
In the fabrication hall, the creation of a large shell and tube heat exchanger begins. This unit, built entirely from stainless steel, is engineered for gas heat recovery at temperatures reaching 500 degrees Celsius, where minimal pressure drop and high durability are essential. The process starts with precision-rolled stainless steel plate, forming the cylindrical shell sections. Each section is welded to create a seamless 7-meter-long body with a 1.5-meter diameter. Expansion bellows are point-welded into position, designed to absorb thermal expansion between the tubes and the shell during operation. Separately, the baffle cage is assembled. Segmental baffles are positioned at exact intervals, providing structural support for the tube bundle while directing gas flow to enhance heat transfer efficiency. Once complete, the cage is inserted into the shell. The tube installation phase follows. 2,900 tubes, nearly 21 kilometers in total length, are inserted one by one. Initially, only the first tube plate is welded. The second plate is then carefully aligned, and the remaining tubes are positioned. Point welding secures them in place before the orbital welding process begins. Welding proceeds in a zigzag pattern, preventing uneven stress on the tube plate. Each tube is then roller expanded to ensure a precise fit and optimal sealing. At the shell inlet, impingement rods are fitted to absorb the kinetic energy of the incoming gas, protecting the tubes from vibration and mechanical wear. Inlet and outlet nozzles are manufactured to strict dimensional tolerances, ensuring seamless integration with the customer's piping network. After assembly, the entire unit undergoes pressure testing under controlled conditions to confirm structural integrity and leak-tight performance. Lifting lugs are welded to the shell for safe handling. Custom saddles are fabricated to support the exchanger during transport. Weighing approximately 14 tons, the finished heat exchanger is hoisted by a 16-ton crane, loaded onto a transport vehicle, and prepared for delivery. Through precise engineering, rigorous quality control, and advanced fabrication methods, the shell and tube heat exchanger is built to withstand the harsh demands of industrial gas heat recovery, ensuring efficiency, reliability, and long service life. The SK18900's closing machine at Jiangsu Safety Wire Rope features advanced strand-laying technology for precise wire rope closure. Its high-torque drive system ensures uniform tension, while automated controls maintain consistent pitch and diameter. Built for heavy-duty steel wire ropes, it delivers high output with minimal tolerance deviations. Producing thin-walled copper tubes with the upcast SG tube process begins with an optimized continuous upward casting method that delivers heavy coils ready for subsequent drawing and annealing. Unlike conventional tube manufacturing, this process bypasses multiple intermediate stages, reducing both cost and energy consumption while maintaining high product quality. The system can also be configured as a hybrid line, enabling flexible capacity sharing between copper rod and tube production to match market demand. The preferred raw material for oxygen-free CUF rod or DHP tube is high-purity copper cathodes. These are loaded into the charging equipment and melted in an electrically heated furnace with channel inductors. Recycled copper may also be used, provided it is exceptionally clean. It requires a longer melting period, making a dedicated scrap melting furnace advantageous to ensure purity and consistency. Furnace configurations vary according to production scale. The single furnace design, compact and open top, integrates melting and casting in one unit, ideal for capacities up to 12,000 tons per year. For higher outputs, the double furnace setup separates melting and casting, handling up to 40,000 tons annually. When both cathodes and recycled copper are used, a triple furnace configuration, 2 melting units feeding a dedicated casting furnace, offers the best performance. All furnaces feature stepless power control, improving efficiency, extending inductor service life, and eliminating harmonic interference from the electrical system. Casting is performed by a multi-strand upcast machine, where molten copper rises vertically through individually cooled graphite dies. The number of strands determines output, and the modular design allows scaling production by adding or deactivating strands without halting operations. Coolers are mounted directly to the casting frame and can be exchanged quickly to switch between product dimensions. The servomotor-driven pulling system lifts the solidifying tube or rod upward from the die, guiding it toward coiling equipment. Rods are typically collected using double coilers for continuous operation, while tubes are directed to single, heavy-duty coilers to preserve their form. The upward casting process produces a fine-grained microstructure with uniform wall thickness, ensuring excellent ductility, dimensional accuracy, and surface finish for downstream processing. This integration of controlled melting, vertical casting, and modular coiling enables consistent, defect-free production of thin-walled copper tubes. The ability to simultaneously cast multiple sizes, change tooling rapidly, and operate with minimal interruption makes the upcast-made same-winterstay process highly adaptable for diverse industrial requirements. By combining efficiency, scalability, and metallurgical precision, this technology provides a sustainable manufacturing route that meets the strict performance standards of modern copper tube applications while minimizing waste and optimizing energy use. Steel is the backbone of modern industry, driving infrastructure, transportation, and countless technologies. In Germany alone, around 44 million tons are produced annually, with steel scrap serving as a key raw material. The Deutsche Edelstahlwerke in Witten are global leaders in high-alloy specialty steels, relying on a massive electric arc furnace to melt scrap and transform it into new steel. Every 90 minutes, operators power up the furnace, unleashing an intense inferno. Temperatures inside soar beyond 1700 degrees Celsius, melting up to 75 tons of material per hour. After tapping the molten steel, the furnace door, still coated in glowing slag, must be cleaned, a task too hot for human hands and handled instead by machines. The journey continues as the still glowing steel blocks move to the rolling mill. There, giant counter-rotating rollers shape the heavy blocks with precision, maneuvered effortlessly by skilled operators using joystick controls. Each year, Witten's plant processes roughly 500,000 tons of scrap into high-alloy steels for the automotive sector, aerospace, medical technology, and offshore wind energy. And when these steel products reach the end of their service life, they may return once again, back into the fiery core of the hell furnace, reborn at 1700 degrees Celsius. Here we go. At Dyrestahl, heavy-duty forging operations handle workpieces weighing up to 45 tons. Two hydraulic 4-column presses of underfloor design deliver pressing forces for up to 40 minutes, enabling deep, uniform deformation. Integrated with rail-bound and free-fall manipulators capable of carrying up to 50 tons, the facility produces axles and drive shafts of extreme dimensions, forged in a single operation with precise gate and bore shaping. Electronic press controls assist operators in achieving consistent results, while a wide range of manufacturing equipment ensures process reliability and cost-optimized production. By combining various stretching and upsetting techniques, the process refines the material structure, enhances mechanical properties, and achieves optimal deformation ratios. This advanced forging setup allows Dyrastol to deliver high-performance components for demanding industrial applications, ensuring strength, precision, and durability in every finished part. The production of large-scale marine cast steel components begins with precision mold preparation. Wooden patterns are fabricated to exact dimensions based on the product's specifications. These patterns are placed inside robust steel frames, and a specially formulated sand mixture containing binders for strength is tightly packed around them. Once the cavity is formed, a mold release coating is applied to prevent adhesion during casting. The mold halves are then aligned and sealed, ensuring dimensional stability during pouring. Melting is carried out in a high-capacity electric arc furnace, capable of reaching temperatures of approximately 600 degrees Celsius. Alloying elements such as manganese and silicon are introduced to achieve the required mechanical properties, while slag and impurities are meticulously removed. The molten steel, referred to as U, is transferred into a large refractory-lined ladle using overhead cranes. Once cooled, the mold is dismantled and the raw casting is extracted. Initial finishing includes removing excess material from the gating and riser system using cutting torches and mechanical saws. Welding may be applied to correct minor surface imperfections. The casting then undergoes multiple inspection stages. Mechanical testing evaluates tensile strength, toughness, and elongation properties. Dimensional accuracy is verified using precision measurement tools. Non-destructive testing methods such as ultrasonic inspection and magnetic particle testing are performed from multiple angles to detect internal or surface defects without damaging the component. Final machining is carried out on large-scale equipment, including vertical and horizontal machining centers. This ensures that surfaces meet strict tolerance requirements and that all functional interfaces are precisely finished. Grinding operations produce a smooth surface finish, reducing hydrodynamic resistance when the component operates underwater. Pouring into the mold is executed with both precision and speed. Accurate alignment between ladle and mold is essential to ensure complete cavity filling without turbulence, which could cause defects. Depending on the size and geometry, the casting is left to cool for several days to achieve uniform solidification and minimize internal stresses. Components manufactured by this process include rudder horns, propeller bosses, and stator fins. Rudder horns, which can weigh up to 4 tons, provide critical structural support for ship steering systems. Propeller bosses, weighing up to 17 tons, house the propeller shaft and transfer thrust forces. Stator fins improve water flow efficiency from the propeller to the rudder, enhancing vessel fuel economy. Through careful control of casting parameters, alloy composition, cooling rates, and machining precision, the process produces high-strength, durable marine components capable of withstanding extreme operational stresses in demanding maritime environments. BM Hafter A small anchor plays a critical role in ensuring the stability and safety of vessels, particularly in shallow waters, coastal areas, and situations where mobility and quick deployment are essential. Despite its compact size, its design and engineering allow it to provide substantial holding power relative to its weight. The primary function of a small anchor is to secure a boat or floating structure in place by embedding itself into the seabed. When deployed, the flukes penetrate the substrate, whether sand, mud, or gravel, using the vessel's tension on the anchor line to increase grip. This prevents drift caused by wind, currents, or waves, ensuring that the vessel remains stationary. In addition to holding position, a small anchor assists in maneuvering and positioning during operations such as fishing, diving, or shoreline maintenance. It allows precise control over a vessel's orientation, enabling operators to maintain a fixed heading or stabilize the craft while working. Small anchors are also widely used as secondary or auxiliary anchors on larger vessels. In this role, they provide additional holding security in adverse weather or challenging anchoring conditions. They can also serve as kedge anchors, helping to refloat grounded vessels or reposition a boat without engine power. The versatility of small anchors extends beyond marine use. They are employed in temporary mooring systems for floating platforms, buoys, and aquaculture installations. In rescue operations, they can stabilize small craft or aid in the deployment of equipment in moving water. Design variations such as grapnel, fluke, or plow-style anchors allow small anchors to adapt to different seabed types. Materials like galvanized steel, stainless steel, or high-strength aluminum alloys ensure durability while resisting corrosion in marine environments. Manufacturing small anchors involves a combination of precision forging, cutting, and welding. High-grade steel is heated in a furnace to the optimal forging temperature, then pressed or hammer-formed into the anchor's shank and fluke shapes. The anchor is then machined to precise dimensions, with edges and tips shaped to enhance seabed penetration. Overall, the small anchor combines portability, ease of handling, and dependable performance. Its effectiveness lies not in its size, but in its ability to leverage mechanical design and seabed interaction to provide secure, reliable holding power in a wide range of conditions. Andritz Hydro Service and Rehab utilizes advanced machinery and systems dedicated to the rehabilitation of hydroelectric plants. This includes high-precision turbine machining centers, generator rewinding equipment, hydraulic cylinder refurbishment units, and specialized lifting and alignment tools for large components. On-site service fleets are equipped with mobile machining stations, balancing machines, and non-destructive testing instruments. These technologies enable accurate diagnostics, efficient component replacement, and optimization of turbine, generator, and control systems, ensuring upgraded performance and extended operational reliability. Acre. Inside the Whitehorse Hydroelectric facility, a 10-year scheduled overhaul is underway on one of its main generators. The process begins with the controlled shutdown of the unit, followed by electrical isolation and mechanical disassembly. Protective covers are removed to expose the rotor, stator, and bearing assemblies. Using heavy lift cranes, the rotor, measuring several meters in diameter, is carefully extracted from the stator housing. This allows full access for inspection of the winding insulation, magnetic core, and cooling ducts. Bearings are dismantled, with journals and bearing shells measured for wear and precision machined where necessary. Technicians perform electrical testing on the stator windings to detect insulation degradation, applying high-voltage tests in accordance with maintenance standards. Cooling systems are cleaned, seals are replaced, and alignment tolerances are checked against original specifications. The rotor undergoes rebalancing to eliminate vibration risks during high-speed operation. After reassembly, the unit is subjected to no-load and load tests, ensuring all parameters meet operational requirements. This comprehensive overhaul extends the generator's service life, improves efficiency, and maintains the reliability of hydroelectric power production for the Whitehorse region. In the heart of Brazil's sugar and ethanol belt, precision metallurgy powers an industry that never sleeps. Within a 70,000 square meter industrial complex, molten steel and cast iron are transformed into components weighing up to 30 tons, each engineered for endurance and precision. The crown jewel heavy-duty milling units designed for the demanding sugarcane process. Each set, weighing around 230 tons, integrates housings, rollers, bearings, juice screens, combs, and other precision cast elements. These machines are built for years of continuous operation, handling extreme loads while maintaining consistent extraction performance. The process begins with high-accuracy pattern development. This stage is critical. The precision of the model dictates the quality of the final casting. From these models, molds are prepared and filled with molten metal. After cooling, parts undergo controlled heat treatment to achieve the required hardness and structural integrity. Manufacturing is a balance of human skill and mechanized precision. Machining, pre-assembly, and finishing are carried out with exacting attention to tolerances. Every movement on the factory floor, from lifting massive castings to aligning roller shafts, is choreographed for both safety and efficiency. Quality control is uncompromising. Tensile strength is measured. Spectrometers verify chemical composition. Magnetic particle testing, ultrasonic scanning, liquid penetrant inspection, and dimensional verification ensure that each component meets strict operational requirements. Only after passing this rigorous process is a milling unit cleared for shipment. Once in operation, the results speak for themselves. Sugar mills equipped with these systems achieve nominal processing capacities of up to 900 tons of cane per hour, with extraction efficiencies exceeding 96.5%. In some installations, they are paired with advanced cane preparation systems, dual choppers and high-capacity shredders, to optimize juice recovery and improve plant productivity. From molten metal to full-scale operational machinery, every step reflects a philosophy of durability, precision, and performance. These are not just machines. They are engineered powerhouses, built to sustain the backbone of an industry that fuels economies. Heavy metal, high precision, relentless quality. This is industrial engineering at its finest, forged in heat, refined in detail, and delivered ready to work for decades to come. Operations commence with the collection and sorting of scrap aluminum from various sources, including industrial waste, used beverage cans, and automotive parts. This scrap is inspected to remove contaminants such as steel, plastics, and dust, ensuring a clean feedstock for smelting. The material is then fed into a pre-treatment system, where any paint, coatings, or residues are eliminated through mechanical and thermal cleaning. Once prepared, the aluminium scrap enters a high-efficiency melting furnace, designed to achieve optimal temperature control while minimizing oxidation losses. The furnace operates with advanced burners and heat recovery systems, significantly reducing fuel consumption and emissions. Molten aluminium is carefully monitored for composition, with alloying elements added as per customer specifications to achieve the desired mechanical properties and performance standards. After alloy adjustment, the molten metal is transferred to a casting unit. Here, it is poured into precision-designed molds or continuous casting systems to form standard-sized aluminium alloy ingots. These ingots are cooled under controlled conditions to prevent internal stresses and improve structural integrity. The production line integrates automated handling systems for stacking, weighing, and marking the ingots, ensuring traceability and quality assurance. Danvanti Engineering's recycling plants are engineered for durability, operational efficiency, and compliance with environmental regulations, delivering sustainable solutions for aluminium alloy production on an industrial scale. In the world of marine maneuvering systems, precision begins long before a boat touches the water. Hidden inside the jet thruster JT90 lies a critical component, the pump impeller, engineered to transform battery power into a powerful stream of thrust. Unlike traditional tunnel thrusters, this centrifugal pump design delivers smooth, quiet, and highly responsive control, making docking and close-quarter navigation both safer and more effortless. The manufacturing process of the jet thruster JT90 pump impeller is a highly controlled sequence designed to ensure durability, efficiency, and precision. The jet thruster system replaces the traditional tunnel and propeller thruster with a centrifugal pump powered by a DC motor. This design, driven by battery power, produces a strong and controllable water jet, enabling pleasure boats to maneuver smoothly and dock safely without complex hull modifications. The heart of this system is the impeller, which must be precisely engineered to perform under demanding marine conditions. Production begins with the creation of the impeller core, which forms the foundation for the casting pattern. This pattern is placed in multi-part molding boxes that arrive at the filling station. A carefully blended mixture of sand and clay is introduced into the mold box. This composition is chosen for its ability to retain fine detail and withstand the high temperatures of molten metal during casting. The mold is then compacted, and the box is flipped to reveal the compressed sand cavity, where the impeller core impressions are clearly visible. Horizontal runners are designed between the patterns to channel molten metal efficiently during pouring. The separate mold sections are precisely aligned and joined together, creating a two-part mold with an exact internal cavity matching the impeller's geometry. Meanwhile, the alloy preparation begins in an induction furnace, which is lowered onto a melting pot containing raw materials. For the jet thruster impeller, an aluminium-bronze alloy is used. This material is selected for its high strength, wear resistance, and superior corrosion resistance in seawater environments. The alloy composition is carefully controlled to meet exact specifications. Temperature is monitored continuously using precision probes, ensuring optimal casting conditions. As the metal melts, impurities and slag are skimmed off to maintain metallurgical purity. The mold incorporates a gating system, which directs molten metal into the cavity with minimal turbulence. This reduces the risk of defects such as porosity or incomplete filling. Once the aluminum-bronze alloy reaches the correct temperature and purity, it is poured into the mold, flowing through the gating channels into the impeller cavities and runners. After solidification, the mold is dismantled, and the rough impeller casting is removed. The gating and runner sections are cut away. The casting then undergoes cleaning, typically via shot blasting, to remove remaining sand and surface residues. Next comes precision machining of critical surfaces, including the central bore, vane edges, and balancing features. Impeller balance is essential to avoid vibrations during operation, which could otherwise reduce efficiency and cause wear to bearings and seals. Dimensional inspections ensure the impeller meets exact engineering tolerances. Once fully machined and inspected, the impeller is integrated into the JT90 jet thruster pump unit. The centrifugal pump, driven by a DC motor, uses the impeller's rotational energy to generate a high-pressure water jet, which is directed through the system's nozzles. This jet provides powerful and precise maneuvering capability, making docking safer and more comfortable. Through this structured manufacturing process, combining accurate pattern making, controlled casting, rigorous alloy preparation, and precision finishing, the jet thruster impeller is built to deliver long-term reliability and high performance in marine environments. The P1040 laser processing system delivers high-precision solutions for cutting and joining glass components in demanding industrial applications. Using ultra-fast lasers, the system achieves clean, micro-crack-free edges without the need for post-processing. In cutting mode, the laser beam focuses energy along a programmed path, inducing localized heating and controlled fracture to produce complex shapes with minimal chipping. For joining operations, precision laser welding fuses glass-to-glass or glass-to-metal interfaces, creating hermetic seals ideal for optical devices, display panels, and laboratory equipment. The P1040 ensures repeatable results through CNC-controlled motion and real-time process monitoring, maintaining exact positioning across large production batches. Its non-contact method reduces tool wear, minimizes contamination, and enables processing of thin or coated glass without compromising surface quality. The result is a fast, efficient, and reliable glass processing solution suitable for electronics, architecture, and specialty glass manufacturing. At Custom Aluminum Products, every extrusion begins its journey as a solid billet, 22 feet in length, weighing over 12,000 pounds, and cast in alloys such as 6063, 6065, 6463 or 6061. These billets, available in 7, 8, or 10-inch diameters, are heated in massive industrial ovens to around 900 degrees Fahrenheit. At this temperature, aluminum reaches a plastic, formable state, pliable under extreme force yet never molten. Once heated, the billet is sheared to an optimal 30-inch section, tailored for the profile to be produced. The extrusion loader positions it into the press, where a hydraulic ram unleashes up to 3,000 tons of pressure, driving the billet into a hardened H13 steel die. The metal flows through the die's precise openings, emerging as a continuous profile with exacting cross-sectional detail. Digital monitoring systems track every step, storing process recipes to ensure consistent results. From the press, a puller grips the hot extrusion, still at 900 degrees Fahrenheit, and guides it smoothly down a 150-foot runout table. Here, high-powered fans cool the profile to room temperature, achieving a T4 temper. Higher strength tempers, such as T5 or T6, are later developed through artificial aging, with water quenching as an optional enhancement. Once cooled, the continuous extrusion is cut by a movable hot saw, separated into lengths, and transferred to the cooling table. Aluminum naturally shrinks and distorts as it cools, so the next stage stretches the profile by approximately 3% of its length. This operation restores dimensional accuracy and eliminates stress. Custom aluminum's dies, up to 15 inches in diameter with as many as 8 profile holes, enable extraordinary design flexibility. With over 12,000 unique profiles produced, the company combines technical expertise with innovative die engineering, delivering optimal performance and cost efficiency in every extrusion. Final stock lengths, often 20 feet or less, are cut with precision on the finish saw before being loaded onto aging carts. In the artificial age oven, controlled heating transforms the alloy into its final hardness and temper. The VLC gear manufacturing line with EMAG's track motion automation system offers a fully integrated, efficient solution for complete gear shaft machining. The process starts with automatic loading of raw parts using the L-shuttle and pickup spindle. In OP10, the first side of the workpiece is turned, followed by OP20 where the second side is machined. After turning, optional post-process measuring can be performed to verify dimensional accuracy and machining quality. Next, the workpiece is transferred to a second translift unit for further operations, OP30 and OP40. In OP30, gear teeth are cut using the hobbing process, ensuring high precision and surface quality. Then, in OP40, the gear is chamfered using the roller chamfering technique to remove burrs and reinforce the gear edges, improving durability and performance. Following machining, the finished workpieces are marked for traceability and automatically stacked into standardized carrier baskets using a loading gantry. This automation ensures consistent handling and optimizes workflow across the entire line. Combining precise machining processes with intelligent automation, The VLC gear manufacturing line minimizes cycle times, reduces manual labor, and ensures repeatable high-quality results, ideal for high-volume production environments in the automotive and industrial sectors. Ever wondered how the memory inside your computer is made? Step into the world of Kingston technology, where innovation, precision, and engineering excellence come together to build some of the most trusted memory products on the planet. Let's take a behind-the-scenes look at how Kingston manufactures its DRAM. Kingston Technology, headquartered in Fountain Valley, California, is the world's largest independent memory manufacturer. It produces a wide range of memory and flash-based storage products, including DRAM, SSDs, USB drives, and embedded chips for mobile devices. With over 2,000 products supporting more than 41,000 devices, Kingston maintains a global presence with 64+ manufacturing lines and a capacity of over 300 million products per year. The DRAM manufacturing process begins in Kingston's engineering department, where product designs are created in CAD. These designs are then tested in compatibility labs on real systems or with advanced test platforms that simulate future hardware. Once validated, designs move into production. Production starts with sourcing components like DRAM, NAND, and controllers from leading semiconductor suppliers. Surface mount technology, SMT lines assemble the modules. The process includes solder paste printing, automated optical inspection (AOI), placement of passive and primary components like DRAM chips, and reflow soldering in ovens reaching up to 500 degrees Fahrenheit. Post-reflow AOI and depaneling follow to finalize the physical modules. What sets Kingston apart is its patented and automated testing equipment. Systems like the KT2100 and KT2500 test hundreds of modules per hour. For server-grade memory, burn-in testing simulates 3 months of intense server usage at 100 degrees Celsius to detect and reject any modules with even one faulty cell. Kingston's strict quality control uses internal and external audits, ensuring adherence to ISO 9001 quality, ISO 14001 environmental, and OHAS 18001 health and safety. Products also meet RoHS and WEEE environmental compliance. Kingston manufactures both its own branded memory and contracted modules for major tech brands, using the same high-quality lines and processes. Once testing and packaging are complete, products are shipped worldwide. Through innovation, advanced testing, and commitment to quality, Kingston ensures reliability and performance in every product it delivers. At Daily and Sunlight, the HDPE double-wall corrugated DWC pipe extrusion line is engineered for high-efficiency production of durable, lightweight pipes used in drainage, sewage, and cable protection systems. The process begins with high-density polyethylene granules fed into a gravimetric dosing system, ensuring precise material ratios. The granules enter a high-performance single-screw or twin-screw extruder, where they are uniformly melted under controlled heating zones and optimized screw geometry. The molten HDPE is then fed into a specially designed co-extrusion die head. This advanced die simultaneously forms the smooth inner wall and the corrugated outer wall. The inner wall ensures low friction and high flow capacity, while the outer corrugation delivers exceptional ring stiffness and resistance to soil pressure. Shaped within a continuous chain-forming machine, the corrugation molds operate under vacuum and cooling water circulation. This guarantees precise geometry and dimensional stability even at high extrusion speeds. Pipe diameters can range from small conduit sizes to large-scale drainage applications, with production speeds optimized for output without compromising quality. An inline perforation unit can be integrated for applications requiring drainage or filtration. Following the forming process, the pipe passes through a water cooling trough to achieve final hardness and stability. Automatic cutting equipment precisely trims each section to the programmed length, ensuring uniformity and clean edges. The system's PLC-based control panel allows real-time monitoring and adjustment of extrusion temperature, vacuum pressure, cooling parameters, and haul-off speed. Data logging functions support production traceability and quality control. Renowned for its reliability and low maintenance, the Dalian Sunlight DWC pipe extrusion line combines energy efficiency with robust engineering, enabling continuous, high-volume output of HDPE pipes that meet stringent international standards for durability, flexibility, and performance in demanding field conditions.
Before a sheet of paper touches your hand, it has already lived a silent journey, growing in sunlit forests, flowing through steel machines, and emerging as a product of nature and technology. Let's uncover the fascinating process behind every page. The paper-making process begins far from the factory floor, in carefully managed and sustainable plantations. Trees such as eucalyptus, acacia, or pine are grown specifically for pulp production. These fast-growing species are planted in cycles, typically harvested every 6 to 10 years. Once mature, the trees are felled, loaded onto trucks, and transported to the pulp mill. At the mill, the logs are debarked, using mechanical rollers and then fed into industrial chippers, producing uniform wood chips. These chips are transferred to large digesters, where they are cooked at high temperatures and pressure using chemicals like sodium hydroxide and sodium sulfide. This chemical pulping process separates the cellulose fibers from lignin, resins, and other wood components. The resulting pulp is washed, screened, and cleaned to remove any remaining impurities. It then goes through a bleaching process, using chlorine-free agents such as oxygen, hydrogen peroxide, or ozone, to achieve the desired brightness while maintaining environmental standards. The clean, white pulp is then mixed with water and enters the paper machine. The slurry is evenly distributed onto a moving wire mesh, where gravity and suction remove much of the water. The damp mat passes through a series of press rollers and heated drying cylinders, reducing the moisture content to around 5%. Next, the continuous paper sheet is smoothed, calendared for consistent thickness and finish, and wound into giant rolls. These rolls are cut into smaller sizes, packaged, and distributed for various uses: printing paper, office supplies, packaging materials, and more. From the planting of each tree to the final roll of paper, every stage is designed for efficiency, sustainability, and precision. This is the modern art of transforming forest fiber into sheets of limitless possibility. From jumbo rolls to perfectly packed reams. Inside the high speed, a 4-paper line in the world of modern office supplies, precision and speed define performance. Behind every crisp sheet of the 4-paper lies a finely tuned, fully automated production line that never stops moving. From massive parent rolls to sealed, bar-coded boxes ready for shipment, this cutting-edge system delivers thousands of flawless reams every hour with zero compromise on quality. This fully automated A4-paper production line delivers high-speed, continuous operation from jumbo roll cutting to final box product. Designed for industrial-scale copy paper processing, it operates at a speed of 220 meters per minute, with an output capacity of 35 to 40 reams per minute, ensuring efficient, uninterrupted production. It starts with unwinding jumbo parent rolls, which are fed into the high-precision rotary sheeter. Equipped with servo-driven cutting blades and optical alignment sensors, the system cuts sheets to the standard A4 size of 210 millimeters times 297 millimeters. Sheets are then accurately counted and aligned into 500 sheet reams using vibration joggers and stacking conveyors. Each ream advances into the ream wrapping machine where moisture-resistant BOP or PE wrapping film is applied. The machine automatically folds, glues, or heat seals the packaging. Inline labeling and barcode printing systems apply branding and tracking data in real time. Wrapped reams are then transferred to the box packing unit, where 5 or 10 reams are arranged into pre-erected cartons. Boxes are sealed using hot melt glue or pressure-sensitive tape and conveyed to the automatic labeling station. A robotic palletizer stacks the cartons according to programmed patterns for easy forklift handling and warehouse storage. The entire line is managed by a centralized PLC control system with a touchscreen HMI, allowing real-time speed adjustment, production monitoring, fault detection, and quick changeovers. Integrated dust extraction, edge trimming, and reject control systems help maintain a clean, high-quality production environment. This A4 paper line is ideal for commercial paper converters, delivering stable operation, minimal waste, and uniform product quality. Its compact structure, high automation level, and output capacity of over 10 tons per day make it a top solution for meeting global demand in the office paper market. In Hungary, witness R+CZRT showcases the production of high-quality rope-handle paper bags using 150 grams per square meter per Graphica paper, known for its excellent printability and luxurious texture. The process begins with precision sheet feeding, where pre-cut sheets of Graphica paper are aligned and fed into the production line. These sheets are then passed through a creasing unit, forming defined fold lines that will shape the body of the bag. Next, the machine applies hot melt adhesive to the designated glue areas, followed by automatic folding into a tubular shape. Side gluing units bond the edges, creating the main body of the bag. Once the bag structure is secured, it proceeds to the bottom forming station. Here, the bottom is folded, reinforced with an inner cardboard piece for added stability, and glued with high-precision applicators. Thanks to fully automated systems, R+CZRT achieves high throughput while maintaining strict quality standards. The use of Graphica paper adds a premium tactile and visual experience, making these paper bags ideal for fashion, retail, and corporate branding. The entire process reflects a balance of craftsmanship, automation, and environmentally conscious materials. The defining feature, the rope handles, are then inserted. Holes are punched automatically, and the reinforced rope handles are mechanically knotted and secured from the inside, ensuring a durable and clean finish. Quality control sensors check alignment, glue positioning, and handle tension at every step. Designed for speed, consistency, and minimal labor input, the fully automatic paper shopping bag making machine delivers an end-to-end production solution for modern packaging needs. With integrated automatic top folding, bottom cardboard inserting, and precise tube forming, this machine ensures the creation of durable and aesthetically refined paper shopping bags suitable for retail, fashion, and boutique applications. It starts with automatic sheet feeding and alignment. Servo-driven systems ensure high positional accuracy, as the machine folds the top edge and applies glue with pinpoint precision. Reinforcement cardboards are inserted at the top section to provide additional structural strength and enhance the overall bag rigidity. Next, the machine transitions into the tube forming and gusset folding stage, where the bag body takes shape. The square bottom is then created, and another piece of reinforcement cardboard is automatically placed and adhered to the base, giving the finished bag exceptional load-bearing capability and stability. Equipped with a PLC-based control system and intuitive touchscreen interface, the operator can easily adjust bag dimensions, glue parameters, and production speed. The machine supports a range of paper grammages and formats, making it highly versatile for various custom orders. With speeds ranging from 30 to 80 bags per minute depending on size and configuration, this equipment significantly boosts productivity while maintaining premium quality standards. Ideal for medium to large-scale manufacturers, the fully automatic paper shopping bag making machine offers excellent value, long-term reliability, and reduced production cost. The price varies based on configuration and optional add-ons, typically ranging from mid to high-tier market levels due to its advanced features and build quality. The Crown RB200 is a fully automated square-bottom paper bag machine engineered for precision, speed, and efficient packaging production. The system initiates from the reel unwinding station, where craft paper rolls are fed into the system. A digital web guiding system ensures perfect alignment throughout the line. The gluing system applies adhesive accurately to critical folding points. The paper then passes through the folding unit, forming the tube structure of the bag. A print mark sensor detects registration marks for precise cutting and folding. In the bottom forming unit, the machine folds and glues the base into a reinforced square bottom, ready for load-bearing applications. Bag counting sensors track each finished bag, while the stacking arrangement organizes them neatly for collection. Completed bags are transferred through the bag delivery unit for packing. The entire process is managed from a centralized control panel, enabling real-time monitoring and quick parameter adjustments. With high-speed operation and precise mechanical coordination, the Crown RB200 is ideal for producing durable, eco-friendly paper bags used in food, retail, and industrial sectors. In Hungary,